Okay, so empirical formula is the most reduced version of a chemical formula. And a molecular formula is the actual, we'll just say non-reduced version. Okay, the molecular formula is the non-reduced version of a chemical formula. So the only time we see a difference with these is in covalent compounds. Okay? Because in ionic compounds, we always reduce them to the smallest version, right? In ionic formulas, we always reduce, if we have subscripts that are reducible, we always do that. But in covalent compounds, like we could have N2O2. That's non-reduced. That would be its molecular formula. But if we were looking at N2O2, this would be the molecular formula. And what would the empirical formula be? NO. Right? It's just the most reduced version of that. Okay? It's the most reduced version of it. So you could have an example. Let's say you're looking at a sample that has the formula PCl3. Is that the molecular formula or the empirical formula or both? Right? Let's say that this is the one we're examining. Like this is the formula we're looking at. Is it empirical, molecular, or both? It's both, right? There's no way it can be reduced any further. We can't reduce this into a smaller version of that. So if this is the one we're examining, right, our molecular is also always like the one we're looking at, right? It's the actual. And so this would be our molecular formula and our empirical formula. Okay? So the rules for empirical formula, once I start telling you the rules, you guys will start remembering this. But I'm going to give you the rule for how we calculate empirical formula. Okay? So usually you start it as a percentage. Usually it will start as a percent composition. Okay? If it starts as a percent, so step 1 would be to convert or switch to grams. Okay, and we're going to act like we have a 100-gram sample. So if it was 40% oxygen, that would mean we just start our math with 40 grams of oxygen. Right? We just pretend like the sample we're using is 100 grams. So when we say convert to grams, it's really not a conversion, it's just a switch, so relabeling. Okay, first things convert to grams. Step 2 to find the empirical formula is, this is an actual conversion, convert grams to moles. Okay, for every element, convert grams to moles. Okay, step 3 of finding an empirical formula. Does anyone remember what the next one is? Divide each, I can't spell, each amount by the smallest number of moles. Okay, that step sounds a little bit, unclear, but it will make sense when we start seeing an example. Once you've done that, once you've divided each mole amount by the smallest number of moles, you'll have a ratio. Those will be your mole ratios to build our compound. One of those should obviously be a 1 because you had to divide something by itself. Right? The smallest number of moles, you have to divide it by itself. So one of those will be a 1. Theoretically, the other ones should come out as whole numbers. But then step 4 would just be to build your formula. Okay, and let me get an example here in our book. Okay, is this ringing any bells? People that had Chem? Not so much? Okay. I think it will once you see how I write the problem, because it was very specific in the way I write it. But okay, we're ready to try one? I know the steps seem super arbitrary until we get an example, and they'll make a little more sense. Okay, so we have an unknown, right? That's why we have empirical formulas, and the way we solve empirical formulas, because we get some unknown sample that we know its mass. We know the percent composition of it, but we don't know what the formula is. When that would ever happen, I don't know, but whatever. Okay, so this one says it's 71.65% chlorine. It is 24.27% carbon and 4.0% hydrogen, right? By mass, those are the percentages. Okay, so since it was given us as a percentage to start, we have to just switch it to grams. Okay, so here's how I kind of write it out. You're going to have to convert them to moles. So I give myself some space. 71.65 grams of chlorine. Make my little T-chart. My next one's 24.27 grams of carbon. And then 4.07 grams of hydrogen. Because I'm going to have to convert them to moles, right? First step was to get them into grams. Second step is go grams to moles. Okay? So now I'm going to go grams of chlorine to 1 mole of chlorine. That molar mass is 35.5. Grams of carbon to moles of carbon. Moles always gets the 1. Carbon's molar mass is 12. And then grams of hydrogen to moles of hydrogen. And hydrogen only weighs 1. Okay. So go ahead and get all the conversions out. This part of it is not the ratio yet. Don't look at these yet in terms of building your compound. We have to still get them to moles, and then we do a division step.
Did we do this when we were at home?
Empirical formulas, I think, would have been before that, but it's possible it was at home.
It was here. Really? Because I did not remember learning this.
I think it was here. This is usually in our chapter for that book in like naming. So it would have been a little bit earlier. Okay, so get our mole numbers, 71.65 divided by 35.5. I would take this out to a few decimal places. So we get pretty exact numbers here. Okay, rounding this part too early could be detrimental. So just keep a few decimal places when we get to those mole numbers. Okay, is that the moles that we had for each? Okay, so our next step is to divide the moles by the smallest amount. So which of these mole numbers is smallest? Right, the top one. Even though these two are really similar, right? We can really think of those as kind of one and the same. But what we're going to do is divide each mole number by the smallest. So 2.018, 2.018, 2.018. So this one obviously comes out to 1. This one comes out to 1.002. So this one comes out to 1 as well. Last one comes out to 2.016. So we want this step of it, we want to come out in whole number ratios, right? Theoretically, they should come out in whole number ratios, which in this case they did. Okay. So now we build our formula, and we build it in the order that our elements were given. Okay, that's generally the rule. We just build it in the order where they were given, which means it would be ClCH2. Right? Is that coming back to us a little bit? I don't really know why in this example it's written that way, because...
Does it matter? Oh, so you get the 2 from the H from that.
This right here tells us that there's twice as much hydrogen as there are this or this.
But for the Cl and the C, does it matter which one comes first?
When in doubt, just list them in the order you're given.
Okay. Yeah. Okay.
I think that carbon should be listed first here because it's technically supposed to go least electronegative to most electronegative, but your book lists it the other way. It obviously doesn't make much of a difference. Okay? I want to give a couple thoughts here in terms of what happens if these don't come out in whole numbers. Okay? Let's say they don't come out in whole numbers. For example, let's say that this one came out to 2.5, right? It didn't, but let's just say for our sake it did. 2.5. That doesn't work. So I have to get this one to a whole number, which means I have to go and multiply the whole thing by 2. So it would be Cl2, C2H5, right? Because we can't have partials. That's how you have to do. You have to multiply the whole thing to get it to a whole number. We don't just round up to a 3. What'd you say?
Well, I don't know why I say balance it, but it distributes it.
Right, it distributes that through there, right.
What do you have to multiply by?
Well, you have to multiply whatever it takes to get it to a whole number. So you would usually double it. It would be rare that we'd get something that comes out to the third, and we'd have to multiply it by 3, but that's possible. You won't ever have to get anything like, you got to multiply by 7 to get to a whole number. Like, it would never come out crazy like that.
So it would never come out like 0.333.
It's possible, but unlikely. Unlikely. Okay? Questions with that? Okay. So let's go back to our actual answer here, which was CCl, ClCH2. That's our empirical formula. So let's say, for an example, we know the empirical formula is this, and we say we have an unknown with the molar mass of 99. Okay, so let's say we know the percent composition, but our molar mass is 99. So what version of this empirical formula are we dealing with? Okay, our unknown has a molar mass of 99. Okay, grams per mole. Okay, so now we've got some unknown. We know the percent composition. We know the molar mass. So we have to figure out, are we dealing with this version? Are we dealing with twice that big? Are we dealing with 3 times that big? Whatever it is. So the way we solve for molecular formulas, okay, molecular formulas. Oops. You take the, one more time. Okay, you take the real molar mass, or the molar mass that's given, divided by the empirical formula molar mass. Okay, so you take the molar mass that was given to you, and we divide it by the empirical molar mass to find out what version of the empirical formula are we dealing with. Are we dealing with the base model, or are we dealing with the 3 times bigger model? Right, that's what we're looking at here. So in this case, the molar mass that was given to us was 99. So that's the molar mass that goes here. So 99 divided by the empirical formula molar mass. So 35.5 plus 12 plus 2. 39.5, is that what you said? 49.5, sorry. Okay. 49.5. So that's going to be in my denominator, 49.5. And we get, this should come out as a whole number, 2. Right? So that tells you that the unknown that we were looking for is twice as big as the empirical formula. Twice as big, right? Because of that 2. So that means our empirical formula was this, but our molecular formula is Cl2C2H4. Okay, does that make sense? Cl2C2H4. Right, just twice as big as this. So that 2 distributes through the whole thing. Formulas. Okay. This stuff should all be reviewed in terms of what chemical reactions are. Okay? Chemical reactions happen when we change something into something new. Okay? Chemical reactions don't happen when something melts or something freezes or whatever like that. That's not when it happens. Chemical reactions happen when something is new. Right? Something forms from something else. It has 2 very distinct parts.
So melting wouldn't be an example of it?
No, because it's still water.
It's still the
Or it's
same.
still whatever it is, right?
Okay.
Still the same. Its identity has not changed.
Okay.
So, 2 distinct parts here are reactants and products. Where are the reactants and products in a chemical reaction? Reactants are on the left. Good, right? Chemical reactions look something like A plus B yields C plus D. These would be the reactants. These would be the products, right? What is that? Actually, I'm going to go over that in a second. Okay, these are what's reacting together to produce this, right? This is what's reacting. This is what is produced. So those are our products. This stuff, if you feel comfortable with it, you don't have to write it down. In chemical reactions, it's so important that you have your formulas right. Because if you are supposed to use lithium sulfite, and you wrote out the formula for lithium sulfate, it's not going to balance, right? You're going to have an extra oxygen somewhere. So chemical formula is super important. Law of conservation of mass must be satisfied. So what does that mean? Say that in a little bit more plain terms. Okay, it can't be created or destroyed. Yes, that's true. Apply it now to our chemical reaction. Has to have equal on both sides. So if you've got 4 oxygen atoms here, have to have 4 oxygen atoms here. Okay, that's it. Symbols we use. SLG are solid liquid gas. You see those next to our formulas. For right now, they don't mean a whole lot to us. Eventually, we're going to start looking at net ionic equations, and those will mean something to us. But for right now, they not so much. What's AQ mean? Yeah, aqueous or aqueous, right? It means it's dissolved in water. That's what AQ means, dissolved water. And then what's the arrow specifically mean? Yields, good. Yields or produces, right? Similar to our equal sign. All right, coefficients. Where do coefficients sit in a chemical formula? At the front, good. So if I have Li3PO4, does that have a coefficient? No, but that gives it a coefficient, right? So this coefficient tells me how many lithium atoms do I have here? 6. How many phosphorus atoms do I have? 2. And oxygen atoms I have 8, right? Coefficients are the only thing we use to balance chemical reactions. When we balance chemical equations, we don't ever adjust our chemical formulas. We can't add a coefficient in the middle, like, I don't want more lithium, so I'm just going to throw it there. Okay, it's got to be in the front of the full formula. All right. This is something that we need to write down. In a chemical reaction, it might tell you oxygen gas or hydrogen gas or something like that. There are some elements that can't exist by themselves. They have to exist in a pair with one of the same. Okay, and so there are 7 diatomic molecules. 7 of them. They even make a 7 on the periodic table. Okay? Oh. They make a 7 on the periodic table. They start right here with nitrogen, oxygen, fluorine, chlorine, bromine, iodide. Okay? Those are your 7. And then hydrogen. So maybe there's 8. I don't know why I said 7. Okay. All right, so if you want to write them down, you can. Okay, but we start with nitrogen into O2, F2, Cl2, Br2, I2, and H2. Oh, no, I'm good. Okay. So this makes a 7 plus hydrogen. Okay? That means if it says hydrogen reacts with whatever, you can't just say H. It has to be H2. So when we start building and balancing our own formulas, we have to give that in the context of H2 or O2 or whatever it is. If it's bonded with something else, it does not follow that rule. It does not have to be a 2. Okay? But if it's by itself, it's got to be 2. Okay. H2 was the very last one in the list. Okay, let's do this top one real quick, and then I'm going to give you this one on the bottom, which is a little bit of a challenge. That'll probably be where we stop today, honestly. Okay, so let's do this top one. When I balance equations, I'll show you the format I use. You can use it if you want. You don't have to. But when I do it, I list my elements in a list, and then I start my count. So on the left, there's 1 aluminum. On the right, there's 2 aluminum. On the left, there is 2 bromine, and on the right, there are 6 bromine. Okay, that's how I start that count. Yeah, Blair.
Do we need to put the...
No, solid, liquid, and gas right now, no. Okay, so I make my list there, and then within my list, I look at which of those is easiest to balance first, right? And in this first one, really easy, right? It doesn't matter which one I do first because they both have an easy change. But let's say if I want to make aluminum 2, I have to add the coefficient. That changes my list. So now I've got 2 aluminums there. I need 6 bromine, so can I put a 6 there? No, what do I need to put? A 3, right? And that makes that 6. So then I look over my list again, and I see, okay, yes, aluminum's balanced and bromine is balanced. Okay, so I like the list format. You don't have to use that if you don't want to. I will always recommend that you do balancing reaction in pencil because there's just a lot of back and forth that goes with that. Why don't you guys go ahead and try this one? This one is a little bit of a challenge. I mean, it took me like a hot minute, but I overshot it, so I'd end up reducing it back down. If it's supposed to be a 1, you can leave it off. I don't make you write the 1 there. I don't care. But whatever it should be, the most reduced version, that's what it needs to be.
In this, aren't there some that are
Yes.
okay with having different, or like not being the same? Or is that in some?